Hi everybody. Today we're gonna continue our discussion on view factor. So in the last video we have already derived what the view factor expression should be based on what we were doing for the past 3-ish videos. Alright, so we've derived an expression for the view factor. So now we want to discuss some properties of view factor and how it can be used. Now, obviously as an engineer you want to find out what the use of a view factor is, right? Well, as you can see, this integral is extremely hard. Pretty hard to compute, even with the simplest geometry, right? Because you have varying angles, and then the dA2 and dA1 will be angled slightly differently at different places, and etc. etc. You might even need a computer to do it. So thankfully there are people who have already done the integration and they put it into these kind of charts. So after integrating, people put the results for certain geometries in charts. This is one such chart from, where is this? MIT. Ooh, must be a very smart chart because it comes from MIT. Just kidding. Anyway, this is the website. Always cite your sources. So this is the view factors, all being charted out for you. So yeah, the integration has already been done. So that's what how you evaluate this integral. All right, so let's use a problem to discuss some of the properties of a view factor. So I'm taking this actually from Fundamentals of Momentum, Heat and Mass Transfer, the 4th edition by James Welty, Charles Wicks, Robert Wilson and Gregory Laurer. Sorry if I pronounced that wrongly. So I'm on one of the examples. Okay, so I'm just going to erase this mess because we don't need it anymore. Okay, so we have a typical problem here. Okay, so we have two plates angled 90 degrees to each other, and then this is surface 1, surface 1, surface 2, this is surface 3, here, 3, there you go. Alright, we want to determine the view factor from 1 going to 2. Alright, and so yeah, what are the dimensions? This is 2 meters. 2 feet, 2 meters doesn't really matter because what matters are the ratios. 3 meters here, 5 meters here. So let's see how we are going to use that chart. Okay, let me use a different color scheme. 5 meter, 2 meter, 2 meter, 2 meter, and 3 meter. Okay, this is a standard textbook problem. Okay, I'm going to select this. I'm going to paste it here. Alright, so let me go and find the citation. Fundamentals of Momentum, Heat and Mass Transfer, 4th edition. Alright, so I'll just put the Amazon of it here. in case you want to buy or something. Okay. So, alright, we don't go in directly integrate, of course, because that's really tough. Instead, we have these guys do it for us already. So, let's see. Okay, so this plane actually gives us z, y, and x, right? They don't give us, like, you know, half of it. Okay, they don't give us half of the plane, so to speak, but we have this dimension being 5 meter, this plus this being 4 meter, and this dimension being 3 meter. So x is 3 meter, y is 4 meter, z is 5 meter. So let's write x equals 3, y equals 4, z equals 5. And how do we get this chart? How do we read this chart? We need a y equals y over x value. So what is y over x? Y over x equals to 4/3 equals 1.33333. Okay. So where will it be? It will be somewhere here, somewhere in between the 1.0 and 1.5 lines. And what is the z over x ratio? So z is 5, x is 3. So z over x equals 5 over 3 equals to, let's pull Excel out. And then we are going to start reading the graph, of course. Oopsie. Yeah. There you go. Gonna zoom in. And let's get our calculator, handy calculator, which I always like to use Excel. 5 divide by what? 3. 1.67. Okay, 1.67. So let's look for z over x equals to 1.67. I'm going to use the pint. 1.67 should be somewhere here. And this y over x equals 1 over 1.33. That will be somewhere here. And what is this view factor? Okay. Okay, I should put it slightly closer to here. So you can see the view factor is somewhat close to 1.9. Okay. So view factor approximately 1.9. Alright. And what is this 1.9? 1.9 is going from this surface 2 to 3 and 1. So normally what people write is the view factor, they put it as f. So it goes from surface 2 to 3 plus 1. And it doesn't matter that which way you go, because you go the other way is the same thing. Oh, wait, this is not exactly the same thing, okay? But there is some relation that we need to know. Okay, let's see again whether we double check our calculations, see whether it's correct. We want to make sure we are getting the right view factor, of course. So view factor for rectangles with a common edge. Wow, that's helpful. Okay. And it just says Fij here. Where is I and j? It's a bit hard to see. Ah, okay. Can you see this here? I'm suspecting this is the weight, since it's from the same textbook. Okay. Come on, snipping tool. Yeah. So we don't know what the view factor is yet, but fi to j. So it's actually 3 plus 1 to 2. Okay. Of course, if you go the other way around, then it'll be slightly different. But I want you to notice something about the integral. Okay, so this is f3 plus 1, which is this bottom going to the top. And we look at our definition again of view factor. Definition of view factor. Okay, this is the definition. And what do we notice? This is the same, this integral is the same, regardless of whether we go from a1 to a2 or a2 to a1. This is a very important thing we must know. So I'm going to highlight this. Okay. And so, what does it tell us? Well, as long as we can find this integral, this f1 a1 equals a constant, and this is also equals to, if you're coming from the other way, f2 a2. So why is this so? Is this because this integral is a constant? Okay, so this is what we call the reciprocity relation. So the view factor are actually reciprocal of each other when you multiply with the area. That is one of the most important things we must know. So okay, we want the one going from 1 to 2. So are we on the right track? Answer is yep. We are going from 3 plus 1 going to 2. Okay, so that's the first view factor we need. Now, the other thing about view factors is that let's say yeah, we can actually split them up. Okay, if we do the integration right, okay, if we do this integration right, we can actually split this bottom integral into two parts, one for the 1 and one for the 3. Okay, so what am I talking about? This integral, all right, it can be split in two. Okay, so let's say it's not just a1 now. You have a1, all right, a1.1 plus a1.2. All right. So this is how we replace, so to speak, our integral. It'll be something like that, because this dA, or rather this is just a1. If you want to split this integral in two, all we have to do is this. Okay, this is the A1. Ah, I see. So I gotta get this out. There you go. So yeah, we want to split this integral in two. All we have to do is here. There you go. So if we want to split the bottom area into two parts, this is what we can do. And what is this? This integral is just f. Okay, so 1.1 going to 2, a 1.1 plus f 1.2 going to 2, a 1.2. That's all we are doing here. All right. So this is the other property of this view factor. Okay, yeah, this is the other property of the view factor. I think I read my graph wrongly. Yeah, view factor should only be from 0 to 1. So that's actually 0.19. Sorry, this should not be 1.9. There you go. Yeah. Alright, so why are we going through all this trouble? Now we want to solve for, let's say, we want to solve for f1 going to 2. Okay, so f, the view factor from 1 going to 2. Okay, but we have the f of 1 plus 3 going to 2. So we can put that in. We can put all this into a formula. F 1 plus 3 going to 2. A 1 plus 3 equals to f 1 going to 2. A1 plus, let's look at the other surface, 3 going to 2. Okay, f 3 going to 2, a3. Now we know this is just 1.9. Oh, sorry, this is not 1.9, 0.19. Where did I get that 1.9 from? Let's be here. Yep, corrected the mistake. So this we can just copy here. Okay, what is a1 plus 3? a1 plus 3 is 2 plus 2 times 3. So 2 plus 2 is 4. 4 times 3, 12. So that's 12 meters square. I'll just put 12 here because the units, after all, they don't really matter. A1, what is A1? A1 is 2 times 3, so let's just put 2 times 3. 6. A3 is also 2 times 3, so that is also number 6. Now we don't know what f1 to 2 is, but we know what f3 to 2 is. Okay, so we can do the same again. We have our z, y, and x. Our z is the same. Our z is 5. Z is 5. Y is 2. X is 3. So, okay, z equals 5, y equals to 2, x equals to 3. So, z by x is still 1.67. Okay, so no change, 1.67. Y over x is 2/3. So let's look for 2/3 on our graph. 2/3, that's 0.6 something. That's 0.67. So we have a view factor somewhere here. So let's give or take 0.27. Alright, not completely accurate, but we're around there. 0.27. View factor 0.27. Okay. Alright, so f1 to 2 can be estimated using the following manner. 0.19 times 12 plus 0.27 times 6, and that divided by 6. So that's 0.19 times 2 plus 0.27. Right? Or is it minus? There should be a minus sign. Again, another careless mistake. Right. 0.19 times 2 minus 0.27 times 2 minus 0.27, 0.11, which is what we should expect, because, well, this 1 going to 2 is much further than 3 going to 2. So because this is closer, there's probably going to be a larger view factor. Okay? Because they are closer to each other, then they cover more of each other's areas. They see more of each other, so to speak. Alright? So that makes intuitive sense. So this is just one application and example problem of a view factor. And of course, yeah, last thing to iterate before I go. Last thing. View factor always ranges from 0 to 1. Why is that so? Yeah, why is that so? You can see all this ranging from 0 to 1, right? Well, the simple explanation is because view factor actually correlates the power received by the second body, let's call it body 2. Body 2 as compared from body 1 compared to the entire power emitted by body 1. That's the rough idea you get here. Okay, so I have a body 2, body 1. Let's put this here. Alright, so this will have some kind of view factor, but this view factor is a geometric representation. Okay, this is just one portion of the entire power, net power being emitted by this body 2. And if you enclose it completely, the view factor is 1. Okay, if enclosed completely, view factor is 1. So these are the last few things I want to reiterate. So we have actually just gone through some example problems of a view factor, a few important properties. One is called this reciprocity relation. One is called like this enclosure kind of a relation here. And of course, it's independent of temperature, etc., etc. So thanks for going through this with me. Hope you've gotten an idea of what view factor is about and how it's actually being used in, let's say, real engineering, so-called real engineering example problem. Yeah. Thanks. See you.